Okay, next we discuss p-n junctions. Okay, but before p-n junction I will revise about p-type semiconductor and n-type semiconductor. In p-type semiconductor or an n-type semiconductor we have more electrons than holes. So the number of electrons are much greater than the number of holes. While in p-type semiconductor we have more holes. I can say we have more holes. Okay, so the number of holes are far greater than the number of electrons. Now electrons are in conduction band and holes are in valence band, and we have the energy band diagram which look like this. If this is the conduction band for the p-n type semiconductor, okay, and if this is the valence band, we have valence band and we have conduction band. The top of the valence band is represented by EV and the bottom of the conduction band is represented by EC. And we have the Fermi energy of n-type semiconductor is close to the conduction band. This is the Fermi energy. And the intrinsic semiconductor Fermi energy is represented by EI, which is at the middle in the middle between EC and EV. Okay, so this is EI, intrinsic semiconductor Fermi energy, while the Fermi energy of extrinsic semiconductor n-type semiconductor is close to the conduction band. This is for n-type semiconductor, while for p-type semiconductor, so we have more holes, then more electron in the conduction band as compared to the hole in the valence band. And we know that this electron will jump from the donor energy level. So if electron jump, then this donor energy level become positive ion, like the arsenic atom. Once they donate one electron, so arsenic atom is a donor atom, and once it's donate one electron, then it requires a positive charge. Now in p-type semiconductor, we have more holes in the conduction valence band as compared to the electron in the valence band. So this is EC, and here we have EV, and the Fermi energy of p-type semiconductor is close to the valence band, so which is EF. We have more holes and few electrons in the conduction band. So this I can be from this video, and in the later video I can represent this n-type semiconductor like this. We have the top of the valence band, conduction band, and we have the bottom of the conduction band, valence band, EV, and we represent the Fermi energy which is close to the conduction band is EI, and here we have the intrinsic Fermi energy, EI. This is the grammatical notation of n-type semiconductor. And here we will represent in a similar way. We have the conduction band and we have the valence band, and the Fermi energy is close to the valence band, EF, while the intrinsic semiconductor Fermi energy is at the middle, EI. Now what is a p-n junction? The p-n junction is a specimen. Suppose we have a specimen or a piece of extrinsic semiconductor which is made of a single crystal, in which there are two adjacent regions. One region is n-type and the other one is p-type. In n-type semiconductor type region we have more electrons, while in p-type region we have more holes. Holes are represented by this circle and electrons are represented by these dots. These are electron and these are hole. So this is n-type and this is p-type. You can say that you take two semiconductor n-type and p-type and you bring them close to each other. You just combine these two pieces. So one piece is n-type and the other piece is p-type. But in practical life, in practical experiment, this is not possible. In practical experiment, we take a single piece of semiconductor in which half side of the semiconductor is doped with acceptor atom and half side is doped with donor atom. So the side which is doped with donor atom become n-type and the side which is doped with acceptor atom is p-type. Now for this one, if we consider this and this is called p-n junction. Now here we plot the band diagram. This is p-type, so it has valence band and conduction band. This is n-type, so it has valence band and conduction band. We have EF. I can write it like this. This is conduction band and this is valence band. Okay. So the top of the conduction band is EC. Here we have EC. This is p-type and this is n-type. Here we have EV and here we have EV. According to these figures. Now the Fermi energy of p-type semiconductor is close to the valence band, while the Fermi energy of n-type semiconductor is close to the conduction band. So here we have this Fermi energy and here we have this Fermi energy. And the intrinsic semiconductor Fermi energy is at the middle of conduction band and valence band. So we have this intrinsic semiconductor Fermi energy which is EI. Now this is the diagrammatical representation of p-n junction, but the variation of donor and acceptor atoms. Suppose we have this x, this is the x distance. On this side we have donor atom which are denoted by Nd. On this side we have acceptor atom like boron which are denoted by Na. So acceptor atoms have a accept electron. Suppose on this vertical side we have Na minus Nd, the difference between acceptor and donor atom. Then on this side we have Na here and the Nd will be here, donor atom. So the N region is doped with donor impurities, the P region is doped with acceptor impurities. The variation of donor and acceptor concentration like Nd and Na across this junction is shown in this given figure. Okay, this is the figure. Now such a junction, like in which the impurity concentration is changing discontinuously, is called abrupt junction. This is an abrupt junction. Abrupt junction. Why? Because on one side of junction we have holes and the other side of junction we have electrons, and the impurity concentration changes abruptly. On inside we have acceptor atom, on the other side we have donor atom, and they change abruptly because the junction, the change is abrupt. and such kind of junction is called abrupt junction. Now the donor concentration is constant in n-type semiconductor and 0 in p-type semiconductor, while the acceptor concentration is constant in p-type semiconductor and 0 in n-type semiconductor. Now the most important thing is, or the most interesting property of the junction is the development of potential difference across the junction, even when there is no even at the junction is at equilibrium. We will explain this concept now, that from where this barrier potential comes from. For that, let us consider, I will go to another figure. Suppose we have a junction, okay. On one side we have electron, on the other side we have hole. These are electrons and these are holes. Here we have hole. Hole are represented by these circles and electrons are represented by dot. This is p-type and this is n-type semiconductor, and here we have this junction. I can write it as a junction, and this is abrupt p-n junction, okay. Like the time when we prepare the junction, at that instant there are only electron in n region and holes in p region at the initial stages. The electric field is zero everywhere, like the electric field is zero everywhere inside this specimen, because the free carriers are balanced by the charge of the ionized impurity. If there are, let's suppose, 1000 electrons, then there are thousands positive ions on this n-type semiconductor. If there are thousands holes, then there are 1000 acceptor atoms, which is negative charge. So they balance each other, so there is no net electric field in this junction. Now the situation is not in equilibrium, however. Despite the absence of an electric field, the electrons are begin to diffuse across the junction from the n region to p region, and similarly holes diffuse from p region to n region. In the last video we just discussed the diffusion current, okay. Diffusion current. In that video we explained that if there are electron concentration are higher on one side of the metallic semiconductor and its concentration is low on the other side, then electron will move from higher concentration to the lower concentration, which is called diffusion current, okay. So here we have more holes, here we have more holes, and here we have more electrons. So what it means? It means that the holes will diffuse from p side to n side, and electron will diffuse from n side to p side. So that I will discuss in the next video, because the length of video is almost 14 minutes and I can't download a video which is a length bigger than 15 minutes. Thank you.